welcome to this problem walkthrough. Today, we'll be exploring problem number 830, titled Positions of Large Groups. This problem challenges us to identify contiguous segments of characters in a string that meet certain criteria. Stick around as we break it down step by step and dive into solving it. In this problem, we are working with a string S that consists of lowercase English letters. Our goal is to identify groups of contiguous, identical characters within the string, which we call groups. Specifically, we are looking for large groups, which are defined as groups where the number of consecutive identical characters is 3 or more. The task is to write a function that returns a list of the starting and ending indices of each large group in the string. These indices should be zero-based, and the groups should appear in the output in the same order that they appear in the string. The input string can have a length anywhere between 1 and 10,000 characters, so we need to design our solution to handle both small and large strings efficiently. The output will be a list of lists, where each inner list contains 2 integers representing the starting and ending positions of a large group. Let's look at an example to clarify the requirements. If the input string is s equals abscc, the function should return 3, 6. Here's why: the substring xxxx forms a large group because it consists of 4 consecutive x characters, which satisfies the condition of having a length of 3 or more. The starting index of this group is 3, and the ending index is 6, so we include 3, 6 in the output. On the other hand, if the input string is s equals abc, the function should return an empty list, because there are no large groups in this string. Each character appears only once, so no group reaches the required length of 3. Another example demonstrates how the function identifies multiple large groups. For the input string s equals abcdddeabbbbcd, the output is 3, 5, 6, 9, 12, 14. Breaking it down, the substring ddd forms a large group with indices 3 to 5. Next, the substring ee is another large group, spanning indices 6 to 9. Finally, the substring bbb is the third large group, found at indices 12 to 14. Each of these groups meets the condition of having a length of 3 or more, so we include all of them in the output. This example highlights how the function must handle cases where multiple large groups exist within a single string. Finally, consider the input s equals AAA. Here, the output is 0, 2, because the entire string itself forms a large group. The substring AAA starts at index 0 and ends at index 2, and its length is 3, which meets the criteria for a large group. Now, let's also keep in mind the constraints and edge cases. The string length can range from 1 to 10,000, and it will always consist of lowercase English letters. The function should correctly handle edge cases, such as strings with no repeating characters, strings where all characters are the same, strings with multiple large groups separated by smaller groups, and strings of length 1. In cases where no large groups exist, the output should be an empty list. These constraints ensure that the solution is both efficient and robust across a wide variety of input scenarios. To solve the problem, one approach we can consider is the brute force method using a sliding window. The intuition here is straightforward: we traverse the string and, for each character, find the longest contiguous substring of identical characters. Once we have this substring, we calculate its length. If the length is 3 or more, we record the start and end indices of this group. The steps involve using 2 nested loops, one to start at each character and another to extend the substring until the characters are no longer the same. While this method is simple to implement, it comes with a significant drawback. Its time complexity is n squared, because, in the worst-case scenario, such as when all characters in the string are identical, the inner loop runs extensively. However, it requires only 1 additional space, aside from the output. This makes it straightforward, but the inefficiency in terms of time makes it unsuitable for larger strings, especially in competitive programming contexts. A more efficient approach is to use a single-pass technique with 2 pointers. In this optimized approach, we eliminate the need to explicitly extract substrings by leveraging the fact that groups of identical characters can be detected when consecutive characters differ. The idea is to use a start pointer to track the beginning of a group and a count variable to keep track of its length as we iterate through the string. When we encounter a transition either at the end of the string or when the current character differs from the next, we check if the group's length is 3 or more. If so, we store the start and end indices of the group. Afterward, we update the start pointer to the current position and continue. This method is highly efficient, with a time complexity of O(n), because we make a single pass over the string. It also uses constant additional space, which makes it optimal. By directly calculating the indices without unnecessary substring extractions, the two-pointer approach is both elegant and effective. The optimized two-pointer approach offers several advantages that make it the preferred choice. First, it is highly efficient, reducing the time complexity to O(n), which is critical for handling larger input sizes efficiently, such as strings with lengths up to 10 to the power of 4. Second, while it is slightly more complex to implement compared to the brute force approach, the underlying logic of tracking group boundaries is clear and avoids redundant computations. Third, it scales well because it uses constant space, ensuring that the solution is both time and memory efficient. On the other hand, the brute force method, though simpler, becomes impractical for larger strings due to its quadratic time complexity, which can lead to significant performance issues. For scenarios like competitive programming, where both speed and scalability are vital, the optimized approach provides the best balance of efficiency and clarity. The key insight that makes the optimized approach so effective is recognizing that groups of identical characters can be identified simply by transitions between consecutive characters. This eliminates the need to extract substrings explicitly, as the start and end indices of each group can be calculated directly during the traversal. The aha moment here lies in realizing that a single pass with two pointers is sufficient to solve the problem optimally. By avoiding unnecessary operations and focusing only on what truly matters, the boundaries of large groups, we achieve both clarity and efficiency. This approach strikes a perfect balance between being easy to reason about and scalable for large inputs, making it an excellent choice for this problem. To start, the problem asks us to identify all large groups in a given string. A large group is defined as any contiguous substring of identical characters with a length of 3 or more. For each of these groups, we need to return the starting and ending indices. Now, the approach we'll use is based on the sliding window technique, which is both intuitive and efficient. The idea is to traverse the string while grouping consecutive identical characters, and whenever the length of a group reaches 3 or more, we record its indices. To implement this, we'll begin by initializing a few key variables. First, we create an empty list called result, which will hold the start and end indices of the large groups we find. Then, we use a pointer I to traverse through the string S. This sets up the foundation for our solution. Next, we move on to processing the string. Starting with I at the first character, we iterate through the string while ensuring that I stays within bounds. To identify a group of consecutive identical characters, we use a second pointer j, which initially matches I. This pointer j will dynamically expand as long as the character at s, j, is the same as the character at s, I, and j remains within the bounds of the string. In doing so, we're effectively grouping all characters that are identical to s, I. Once j reaches a point where the characters differ or the string ends, we calculate the length of this group as group_length equals ji. If this length is 3 or more, we know it's a large group, and we append the tuple I, j1, to our result list. Finally, to move to the next group, we update I to j, skipping over the characters we've just processed. After processing the entire string, the last step is to return the result list containing the start and end indices of all the large groups we've identified. The sliding window approach we used is particularly effective here because it allows us to dynamically expand the window as needed while skipping unnecessary sections of the string. Now, let's consider some insights about why this approach works so well. The sliding window mechanism efficiently groups consecutive characters without revisiting or reprocessing any part of the string, ensuring that we only traverse the string once. This results in a time complexity of O(n), where n is the length of the string. Additionally, each operation, such as checking the group length or appending to the result list, is performed in constant time, making the overall algorithm highly efficient. When implementing this algorithm, it's important to consider certain edge cases. For instance, if the input string is empty, there are no groups to process, so we simply return an empty list. If there are no large groups in the string, the result is also an empty list. Another scenario is when the entire string forms a single large group. In this case, the algorithm still works correctly, as it will identify and record the group's start and end indices. Overlapping groups don't occur due to the way the pointers I and j traverse the string, ensuring non-overlapping processing. Additionally, the choice of data structures is crucial for efficiency. We use a list to store results because it allows for quick appending, and the two-pointer technique with I and j ensures that we avoid redundant traversals, keeping the algorithm streamlined. Let's go through an example to see the algorithm in action. Suppose the input string is s equals aebc. First, we initialize result as an empty list and set I to 0. The first group consists of the characters AAA. Starting with j equals 0, we expand the group by incrementing j until the characters differ, so j becomes 1, then 2, and finally 3. The group length is 3, so we append 0, 2 to the result list. We then update I to 3 to move to the next group. The second group consists of BBBB. Here, j starts at 3 and expands to 4, 5, 6, and 7. The length of this group is 4, so we append 3, 6 to result. Once again, we update I to 7. Finally, we examine the third group, which consists of the characters CC. Starting at j equals 7, we expand j to 8 and 9. However, the group length is only 2, which is less than the required threshold of 3, so we skip this group. At this point, I is updated to 9, which is the end of the string. With no more groups to process, we return the result list, which contains the indices of the large groups 0, 2, 3, 6. This concludes the walkthrough of the example, demonstrating how the algorithm efficiently identifies large groups while handling all edge cases and ensuring optimal performance. This code solves the problem of identifying large groups in a given string where a large group is defined as 3 or more consecutive identical characters. The implementation uses a single pass through the string, making it efficient with O(n) time complexity. We define a solution class with a method large group positions. The method takes a string s as input and returns a list of starting and ending indices for all large groups. We initialize an empty list result to store the indices of large groups, and a variable start to track the beginning of each group. The for loop iterates through the string using indices from 1 to n plus 1. The condition I equals n or s, I equals s, start, checks if the current character ends a group, either due to reaching the end of the string or encountering a different character. If the group is large, i.e., its length is at least 3, we append its start and end indices to the result list. The start variable is then updated to I to begin tracking the next group. Finally, the method returns the result list containing all large group positions. This implementation handles edge cases like strings with no large groups, strings consisting entirely of one character, and empty strings efficiently. It minimizes space usage by only maintaining the list of results and a few pointers, ensuring the solution is both clean and efficient. This is the Java implementation of LeetCode problem number 830, positions of large groups. The logic mirrors the Python solution, using a loop to identify groups of consecutive characters and checking if their size meets the large group condition, 3 or more. Key differences include explicit type declarations and usage of Java-specific collections like ArrayList and Arrays.asList for storing results. We begin with the input string s equals abscc. First, we initialize our variables. Result is an empty list to store the positions of large groups, n is set to 10 as the length of the string, and start is initialized to 0 to mark the beginning of the current group. Now, as we start iterating through the string, at I equals 1, we notice that s, I, is b, while s, start, is a. Since the characters are different, the group ends here. The size of this group is id start, which equals 1. Since this is smaller than 3, it does not qualify as a large group, so we move the start pointer to 1 to begin tracking the next group. At I equals 2, s, I, is still b, which matches s, start, so the group continues without any changes. At I equals 3, the character s, I, changes to x, while s, start, is b. This indicates the end of the current group. The group size is calculated as I start, which equals 2. Since this is less than 3, it is not a large group, so we update start to 3 to track the new group. As we proceed, for I equals 4, I equals 5, and I equals 6, the character s, I, remains x, matching s, start, so the group continues uninterrupted. At I equals 7, s, I, changes to z, which ends the current group. The group size is now I start, which equals 4. Since this is at least 3, it qualifies as a large group, and we add the range 3, 6 to the result list. After this, we set start to 7 to track the next group. For I equals 8 and I equals 9, the character remains Z, so the group continues. When we reach I equals 10, which is the end of the string, the current group concludes. The group size is calculated as I start, which equals 3. Since this is at least 3, we add the range 7, 9 to the result list. At this point, we have finished processing the string, and the final output for this example is result equals 3, 6, 7, 9. Next, for the second example, we take the input s equals abc. We initialize our variables again. Result starts as an empty list, n is set to 3 as the length of the string, and start is initialized to 0. As we iterate through the string, at each step, the character s, I, differs from s, start, indicating the end of each group. The group sizes are all 1, which are less than 3, so no ranges are added to the result. After processing all characters, we update start at each step but find no large groups. Once we reach I equals 3, the end of the string, we confirm that there are no groups of size 3 or larger in this input. Therefore, the final output for this example is result equals. Now, for the third example, we use the input s equals ABAC. Starting with initialization, result is an empty list, n is set to 10 as the string length, and start is initialized to 0. As we begin iterating, at I equals 4, the character s, I, changes to b, while s, start, is a, marking the end of the first group. The group size is I start, which equals 4. Since this is at least 3, it qualifies as a large group, so we add the range 0, 3 to result. We then update start to 4 to track the next group. At I equals 8, the character s, I, changes to c, while s, start, is b, indicating the end of the current group. The group size is calculated as I start, which equals 4. This qualifies as a large group, so we add the range 4, 7 to result. Next, at I equals 10, which is the end of the string, the current group ends. The group size is I start, which equals 2. Since this is less than 3, it does not qualify as a large group. With all iterations complete, the final output for this example is result equals 0, 3, 4, 7. The time complexity of this solution is O, n, where n represents the length of the input string s. To break this down, the solution uses a single loop that iterates through the string from start to finish. This loop runs exactly n times, performing a constant number of operations during each iteration. For example, within the loop, we check whether the current group of characters has ended. This is a straightforward condition that operates in O1 time. Similarly, when we evaluate whether the group qualifies as a large group by checking its size, that operation is also O1. If the group is large, we append the start and end indices to the result list. Appending to a Python list is an amortized O1 operation as well. Since the loop processes each character in the string exactly once, and all operations within the loop are constant time, the overall time complexity of this solution is O(n). The space complexity of the solution is O(m), where m is the number of large groups in the input string s. This is because the result list needs to store the start and end indices for each large group. For every large group, we store a pair of integers, which means the space required grows linearly with the number of large groups. Besides the result list, the solution uses a few temporary variables, such as n, start, and I, which each take constant space, or O(1). Importantly, the input string s is read-only, so it does not contribute additional space usage. Therefore, the dominant factor in space complexity is the result list, leading to a total space complexity of O(m). In terms of best, average, and worst-case scenarios, the time complexity of this solution remains O(n) in all cases because the loop always iterates through the entire string. However, the space complexity can vary. In the best case, if the string contains no large groups, the result list remains empty, so space usage is O(1). In an average scenario, where the string contains a small number of large groups, the space complexity becomes O(m), where m is the number of large groups. Finally, in the worst case, if the string is composed of a single repeated character, it forms one large group. This means the result list will store only one entry, and the space complexity is O(1). Regardless of the scenario, the time complexity remains O(n), as the loop processes the string in a single pass. When comparing this optimized solution to a naive approach, we can see significant improvements in both time and space complexity. A naive approach might involve iterating through the string multiple times to explicitly count consecutive characters for each group, which would result in a time complexity of O(n) squared, due to nested iterations. In contrast, the optimized solution processes the string in a single pass, achieving O(n) time complexity. Additionally, the naive method could use unnecessary intermediate data structures to store group information, potentially increasing space complexity. The optimized solution avoids this by directly appending results to the output list only when a large group is identified, ensuring the space complexity remains O(m). Mathematically, the single loop iterates n times with constant time operations per iteration, confirming the overall time complexity is O(n). Similarly, the result list grows linearly with the number of large groups, resulting in a space complexity of O(m). When tackling this problem, there are several common mistakes to watch out for. First, not accounting for edge cases is a frequent pitfall. For example, strings that are empty, contain only a single character, or don't have any large groups at all can cause runtime errors if not handled correctly. Always include these scenarios in your test cases. Another issue arises with incorrect sliding window implementations. If you're using this approach, it's essential to keep the window boundaries properly updated, otherwise, you might skip valid groups or include invalid ones. Misinterpreting the definition of a large group is another challenge. Remember, a large group means 3 or more consecutive characters, not strictly more than 3. Inefficient solutions can also be problematic. Using nested loops to check substrings results in O(n) superscript 2 complexity, which is impractical for large inputs. Finally, off-by-one errors are common when calculating group boundaries or lengths, so double-check your conditions to ensure accuracy. Now, let's consider some insights that are particularly useful in interviews. This problem is designed to assess how well you can identify repeating patterns in a string. Using pointers or indices to efficiently track contiguous characters is a critical skill here. Interviewers often include edge cases to test your robustness. Examples include strings with no large groups, strings made entirely of the same character, or very long inputs. Being prepared to handle these gracefully can set you apart. Additionally, if the interviewer asks about alternative solutions, be ready to explain trade-offs. For instance, you could compare a brute force approach to more optimized techniques like sliding windows or two pointers. Lastly, focus on code readability. Clean, modular code not only makes debugging easier but also demonstrates your ability to write maintainable solutions. Related problems that build on similar concepts include LeetCode 830, which is the problem we're discussing here, as well as problems like longest palindromic substring and longest substring with at least k repeating characters. Exploring these can deepen your understanding of substring-related logic. There are multiple approaches to solving this problem, each with its own strengths and weaknesses. The brute force method involves checking all substrings of length 3 or more. While this approach is straightforward and easy to implement, it has a time complexity of O(n) superscript 2, making it inefficient for larger inputs. A more optimized solution is the sliding window or two-pointer technique, where you traverse the string once while maintaining pointers to track group boundaries. This approach is efficient, with O(n) complexity, but requires careful boundary management to ensure correctness. Another alternative is the single-pass grouping method. Here, you use a single loop to count contiguous characters and save the start and end indices of groups that meet the threshold. This method is also highly efficient but might be less intuitive for beginners. Finally, regex matching can be used to identify large groups in a concise manner. However, this relies on external libraries like Python's re module, which may not be permitted in an interview setting. While regex is clean and elegant, it's less performant and doesn't showcase core algorithmic problem-solving skills as effectively. That wraps up our problem walkthrough. We explored a brute force solution using the sliding window technique and highlighted its potential for improvement. Remember to practice similar substring problems to strengthen your understanding. Thanks for watching, and don't forget to like, share, and subscribe for more content. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!